So for investigation 2, we will do a quantitative analysis of the data we've collected. I'm displaying on the graph here the velocity the velocity and the acceleration data from the first run when the fan was at a medium speed. Go ahead and sketch these graphs onto your into your lab book. I'll apply a little smoothing here to the acceleration graph. And so what you should end up seeing is something more flat like that. Okay. Now, what we're going to do first is we need to find the average acceleration of the entire run. And so what we're going to do is we will use our coordinates tool and we will pick 10 data points. We will pick 10 data points to find the acceleration of the cart. So let's start off. We will go to the coordinates tool. We'll use the multi-coordinates tool and we'll read the data off of that. So let's start off with the first acceleration is 0.33 meters per second squared. Then we'll go to 0.34 meters per second squared. And you're going to go ahead and write this data down into your lab book. 0.34, sorry, 0.34. That point there, that makes it 0.28. And our fifth point is going to be 0.32. Our sixth point is 0.29. Seventh point will be 0.26. Eighth is 0.22. And ninth will be 0.25. And the last data point will be 0.37. Okay. Now again, all of this information, all of these numbers, completely random. So we've selected the coordinates tool. Copy the data points onto page 38 of your lab book. Find the average of your 10 points and record it. So I'm going to go ahead and punch it into my calculator here. So 0.33 plus 0.34 plus 0.34 plus 0.28 plus 0.32 plus 0.29 plus 0.26 plus 0.22 plus 0.25 plus 0.37 gives us a total of 3. We divide that by 10 data points, and that gives us an average acceleration of 0.30 meters per second squared. Okay? Now, the average acceleration during a time interval is defined as the average rate of change of velocity with respect to time. In other words, the change in velocity divided by the time interval of the change. By this definition, the rate of change is quantitatively graphed with respect to time as the slope of the graph. Thus, the slope of the velocity versus time graph should be the average acceleration of the object. So what I'm going to do is, as you can see, I have position here. I'll just change that over so that we can see velocity. I'll leave that unsmoothed because, as we know, the entire run of data is the motion of the cart. So what I'm going to do is find the coordinates. So let's start off the first coordinate at time 0 seconds has a velocity of 0.31 meters per second. Our next coordinate will be this point, and it was at a time of 1.52 seconds and had a velocity of 0.76 meters per second. Okay? Next, we need to find the change in the velocity in the time interval. The change in velocity is going to be 0.76 minus 0.31, which gives us a change of velocity of 0.45 meters per second. The change in time, or the time interval, well, since the first one is 0, the second one is 1.52, so our time interval is 1.52 seconds. So if we take the first, the 0.45, divide it by the 1.52, we end up getting an average acceleration of 0.296 or 0.30, which is very close. That leads us to question 2-1. What is the acceleration positive or negative? Is this what you expected? Question 2-2. Does the average acceleration you just calculated agree with the average acceleration you found from the acceleration graph? Do you expect them to agree? How would you account for any difference? In addition, now there's an activity 3-2, speeding up more. What we can do is we can use the run2 data. And for the run2 data, all I need to do is just change that to run2 and apply smoothing to the acceleration graph. Right, that'll work out there. And now we can go ahead and put in that data. So for run2, let's go ahead and calculate the average acceleration. Let's use the coordinate tool. And we'll start at that point. So we'll go 0.56. The next data point will be 0.55. The next data point will be 0.57. Then we'll jump on over here to 0.54. Over here, 0.57. Let's go over here, 0.45. We'll keep going. 0.40. We've got 3 more data points to do, so let's go 0.40 here. We'll do this one here. That gives us 0.50. And we'll just do the very next one, and then it gives us 0.96. Oh, I'm sorry, 0.61. I'm reading the wrong numbers. Okay, so what's the average acceleration? Okay, 0.56 plus 0.55 plus 0.57 plus 0.54 plus 0.57 plus 0.45 plus 0.40 plus 0.40 plus 0.50 plus 0.61. Divide that by 10, and we get an average acceleration of 0.515 or 0.52 meters per second squared. Compare this average acceleration. Okay, does the average acceleration calculated from the velocities and the times agree with the average acceleration you found from the acceleration graph? And how would you account for any difference? And compare this average acceleration with that of the slower fan, which is larger, and is this what you would expect? Let's go ahead and find the average acceleration from the slope. And again, what we'll use is the first number is going to be 0.40 for the velocity. The final velocity is going to be 0.99. So therefore, we got 0.59 for our change in velocity. The time interval is much shorter, 1.12. So, again, not 0.59, 0.9 is 0.99. There we go. So, 0.99 minus 0.4 gives us 0.59 meters per second. And we're going to divide that by the time interval of 1.12. And that gives us an average acceleration of 0.526 or 0.53. So in the previous one it was 0.52. This one is 0.53. Looks to me like that's a pretty good agreement between the two. Let's go ahead and do one more thing. Let's go ahead and do the extension 2-3. We'll go ahead and use the tools available on the computer in order to find the average acceleration. Let's go back to run number 1. Let's see. So we go back to run number 1, And do we have smoothing on that one? I cannot tell. Yes, we do. Okay. Oh, that's the problem. All right. The problem is can't see 0, so we have to scroll out. There we go. Now it makes a little bit more sense. Now you can see from 0 to 0.8 on the acceleration. So first off, what is the average acceleration? Let's use the statistics function. And we see the average acceleration is 0.31. What is the average acceleration from the velocity graph? We'll use the line fit. And we see the slope is 0.32. So that sounds like a pretty good agreement. Okay. Now, what about for the other one? What about for the faster run? Well, for the faster run, we'll just change it to run 2. The average acceleration turns out to be 0.55. And the average acceleration based on the slope of the velocity line becomes 0.41. I'm sorry, I was reading the intercept. It's 0.515. Very close agreement to what we calculated out in the previous part of the chapter. Okay, so what are we trying to get here? Simply put, if the acceleration is constant, the average acceleration is going to be the average of the accelerations. And again, if the acceleration is the average acceleration in any time interval is the change in velocity divided by the time interval or the slope of a line made between those points. This finishes up investigation 2. And our next one, investigation 3, we're going to see what happens when we change the direction of that the fan blows with respect to the motion sensor.